Okay, okay. As you can see over there, I'm going to be taking you through Newton's laws of motion. So definitely, I'm not going to waste much of our precious time. Straight away, I will tell you something very much important, honorable member, to say forces. Let me just start there and say forces. It's exactly what we are going to be talking about. But maybe let's talk and ask ourselves a question to say, what exactly is a force? So a force, it should be a push or pull. I hope you are listening very carefully, honorable member. It's either you are pushing or pulling. It could be an object which you are pushing or pulling. That action, honorable member. So that action whereby it is a push or a pull action exerted on an object by another, it is therefore being referred to as a force. So I'm just hoping that that part alone is clear. Push or pull, nay, exerted on an object by another object. That is a force. So this action, honorable member, it can be exerted while the two objects, it could be two or more, they can be in contact or not in contact. So that means that action of push or pull, it can happen while one object is acting on another object, either over a distance or while they are in contact. I'm definitely going to make some more sense as we continue. So let's just categorize these forces into two types of forces. Maybe let's talk about the contact forces. Yes, maybe let's talk about the contact forces. And then on the other side, maybe we will talk about definitely non contact forces. So I will need you to pay maximum attention because what I'm going to explain, very much important, honorable member. And with regards to the Newton's laws of motion, this is where they start. This is the best way to start this chapter. So with regards to the contact forces, so a force exerted between objects that are in contact with each other. This is what we talk about the contact forces. So that means the non-contact forces, this is where a force exerted between objects over a distance without physical contact. Maybe in terms of the examples, we can talk, for example, about applied force. So applied force in physical sciences, we will therefore refer to that as F, and you will see we will do that smaller than a there. So that is the applied force. And the other one, it could be a tension. So maybe with regards to the applied force, it is normally the one where you either push a person or you are pulling that person. That just think of that as an applied force, where it's either you push the other honorable member with your hand or you pull their hand. So the push and pull, we will therefore refer to that as the applied force. And this one of the tension, normally we just write capital letter T, which refers to the tension. That's why, for example, you'll be having a truck towing a car. So that rope between the two cars, you see, it is the one that makes those two objects to be in contact through that a rope. It could be a rod, whatever the case may be. So that's what we talk about when we are referring to the tension force. And then number three, can you think of number three? The frictional force, yes, the frictional force. So This is another type of a force by friction. So you will see for this one, we do that capital letter F, and then we do small f there, which refers to the frictional force. Maybe let's not do too many where we will end up complicating things. We'll just leave it at that fourth one being the normal force. I will definitely explain what the normal force is. And normal force. Normally, for the normal force, we can just do capital letter N there. Or maybe sometimes even if you see a capital F for the force and then small n there, it refers to the normal force. Okay, just to add, with regards to the frictional force, sometimes you will see they can say that F and then they can do S there. Otherwise, if not that one, they can do that F and then K there. I will explain that as we continue. So these are the types of contact forces that you might need to be aware of. The contact forces being a force exerted between objects that are in contact with each other. What about the non-contact forces? Maybe let's start off with this one called gravitational force. I'm pretty much sure that by now you've got an idea of what that is. Gravitational force. So how we represent this one, it is by that capital letter W, which refers to the weight. Otherwise, we can do that capital letter F and then G there, which is an indication that here we are talking about the gravitational force, which is as a result of force of gravity. And then the second one under a non-contact force. What else can we talk about? We can even talk about electrostatic force. And we will get to this topic, but just be aware that electrostatic force, it is also another type of a non-contact force. And then the other one, it is the one for a magnetic force. Yes, magnetic force, of which another topic on its own. So under Newton's laws of motion, these are the most important forces that we are going to be talking about. Just these 5 forces. These other ones, it was just for your information to be aware that we've got types of forces, the contact forces and the non-contact forces. Very, very much important on that one, honorable member or the member who is honorable. So now I would like to talk about the normal force, because all these other forces, I think they are self-explanatory. The applied force, the you being the pushing or the pulling guy, then you are having the tension there, 2 objects connected by a rope, and then we have the frictional force. Obviously, as an object is moving, it experiences that frictional force. So I think I will also have to explain more about frictional force and also the normal force. That one of the force by gravity, I think it is also a straightforward one, especially that it even has a formula, that one, whereby we just say force by gravity is equals to the mass of an object multiplied by the gravitational acceleration. So that one of the electrostatic force and magnetic force, it's something else, new topics or topics on their own that we will look into as we continue. So, okay, for now, let me start with this one of the normal force. Actually, what exactly is a normal force? Let's just start there. Say normal force, which is that. Okay, so this is the perpendicular, very much important, the perpendicular force exerted by a surface on an object in contact with it. Even if we don't mention in contact with it, it is well known by now that a normal force is a contact force. So the definition of normal force would be, let me just write it down to say, the perpendicular, very much important to include that in your definition of a normal force. So it is therefore a perpendicular force which is exerted by a surface on an object in contact with it. In contact with it. Yes, something of this nature, honorable member. So the normal force is equals to the perpendicular component of gravity. That's if there are no other forces acting on that object. Let me give you an example, honorable member, to say, if you are having a table, and on this table, you are having your calculator there. Nay. So this is what happens, honorable member. That calculator, it is not moving. It is just stationary on the table. But trust me when I say there are forces that are acting. And these are the forces, honorable members. You've got this vertically downward forces, which is always existing and acting on every object. And this force, it is the one that is called force by gravity. Or otherwise, even if you say the weight, you are still right in saying that. This force, it is always there. That is why if you can just take that calculator and leave it somewhere in the air, so it's like you lift it up above the table. If you release it, it is going to hit that table because there is a force which is pulling it downwards towards the table. And that force, it is the non-contact force because it is not in contact with that object, but it is able to therefore pull it towards the center of the earth or towards the table. That's why it will moor that table. After mooring that table, it will not continue downwards. But what's going to happen is that it will just remain on the table. Why? Because the table is applying a force on that calculator. And this type of a force, which is applied by the surface, it is the one that we call the normal force. I hope this part makes sense, honorable mem. So that's why I'm saying the normal force, it is actually the perpendicular force exerted by a surface. Very much. So we say perpendicular force because it forms the 90-degree with the surface. That is very, very much important. That's why we refer to that as the perpendicular force exerted by the surface on an object in contact with it. So I hope that part makes sense. So in terms of a formula, that is why we can therefore make a conclusion to say, since this calculator is not moving, it is stationary, it is there on the table. So that means the force that is exerted by the gravity, it is equals to the normal force. So this is therefore the formula that we can use to describe that situation. In other words, it means the formula for calculating the normal force, it is equals to the formula for calculating the force by gravity, which is equals to the mass of an object multiplied by the gravitational acceleration. But obviously, it will be in the opposite direction. As you can see, gravity downwards, but the normal force in the opposite direction, but having the same magnitude. You need to be careful of my statement, honorable member. This formula is valid only if you don't have another force acting on that object. That is very, very much important, honorable member. So that means what I'm talking about now, it's a situation whereby you just have a calculator and the only force acting on that calculator, it is the one by force of gravity. And because that is on the table, then the table, it is the one that is applying the normal force. It's like it's a force that is reacting to that one of the gravitational force. And that force, it is exerted by the table. So I hope you fully understand this part when I say there we are not having any other external force, but it is just that force. So maybe let's look at another situation so that you will have a better understanding of what I'm talking about. So if alternative force act on the object, so the normal force will definitely change, and this will depend on the direction and magnitude of that applied force. So that means all the vertical forces must be balanced if there is no acceleration in the vertical plane. Maybe just to diagrammatically explain what I'm talking about here, let us say you are having that same table. And with you having that same table, let's say here we are having a box right on that table. Nay. And we are saying there is a pulling force. You can see that this is an arrow away from that object. So we refer to this as applied force. Even though there is an applied force pulling, it doesn't necessarily mean that this object is moving. So just think of it as a pulling force, whereby as it is pulling this object, it doesn't necessarily move that object. So it's a force, but a smaller force pulling that object, even though that object is not moving. It is still stationary there. Yes. Okay. Then it's fine. So let's now identify all the forces acting there. So that means here you will have that force which will always be there, which is force by gravity. And you will definitely have this one by the table, that perpendicular force. And this one is called the normal force. And you also have this one, but that one, it's acting at an angle. So that means the vertical component of this force, it is that one, if you remember, whereby you will be having that whatever angle there, because this force, it is acting at a certain angle. So that means the vertical force will be that one of that force applied sine of an angle. Because if you are having that 90-degree there, the vertical force, it is the one which is the side opposite to that angle. If we were talking about the horizontal force, it would therefore be this one for the cos of an angle. So now let us try to look at the formulation with regards to having this type of forces. So that means we are having now the normal force, obviously in the upward direction. We also have that component of the applied force in that vertical or upward direction, which is force applied sine of an angle. And we will therefore equate this to force by gravity. So it's like we are taking all the upward forces, we equate with the downward forces. Why? Because they are balanced. How do I know they are balanced? It's because I mentioned to say this object is not moving. It's not moving up, it's not moving to the right, it's not moving down, not moving left. It is just stationary there, even though we've got multiple forces. So that means now, if we had to make the normal force the subject of the formula, we therefore have normal force being equals to force by gravity, but this time around, minusing that force applied, multiplying by sine of whatever angle there. So can you now see that in a situation where we have an external force, the formula for the normal force, it therefore changes. So this is the situation in which it changes as a result of the component of that applied force. So that means here I just formulated on a situation where we had a pulling force, and that pulling force, it was pulling at an angle. What about if we are having a pushing force? So that means, again, we are having that table, and very quickly, let me draw that. So that means a pushing force would be this one at an angle, still being applied force, obviously acting at that angle theta. So that means in this case, we will have this force that will always be the force of gravity. And then because this object is on a surface, the surface will also apply that 90-degree force there being the normal force. In terms of formulation, it will therefore mean the component of that applied force, it is therefore the one that is acting downward, unlike the one of a pulling which is acting upward. So the component for this one, it is the one that is acting downward, which means in terms of the formulation, we are therefore going to say in terms of the vertical forces, we have the normal force acting upward. So that means I'm always assuming my up to be positive, my down to be negative. That is why I'm saying positive n, because the arrow points upward, and then the arrow for this one is downward. So that means for this one of the component, you just need to remember that it is not the applied force, but it's the applied force sine of an angle, because it's acting at an angle. Therefore, it will therefore be minus a force applied there, having sine of an angle, which will therefore be equals to mg. Why? Equal because this object is still not moving. It is just stationary there, equals to fg. Therefore, it means the normal force will therefore be equals to fg, but this time around you plus, because you take it to the other side, it becomes a force applied sine of an angle. And this should be the formula where you are having an applied force which is pushing or acting in that angle. So I hope that part makes sense, honorable member. Maybe let's see, what about object suspended from a rope? It could be a string or a cable, it doesn't really matter that much. So that means those ones, they don't have normal force. Why? Because they are not necessarily resting on a surface. So just think of that being a ceiling, and then you are having a, what is it? Let's say a light bulb there. Yes, you are having that light bulb there. So in this situation, honorable member, you are just having a force in that direction by that cable. It could be a string or a rope. So that's where we talk about the tension. And then the other force that you are having, it is this one that will always be there, being a force of gravity. So that means this time around, we will say force by that tension, it is the one which is equals to force by gravity, because that light bulb, it's not like it's falling, and it is just stationary at that position. It's because these two forces are balanced. Therefore, there is no normal force. Why? Because it's not like this object is on a surface where we were going to say there is a normal force in that direction. There's no normal force where you are having a situation like this. So I hope that part makes sense, honorable member. Maybe very quickly, as I wrap up, I will therefore just explain to you regarding this type of a friction being not a frictional force where we've got a static friction and kinetic friction. I will just make sure not to confuse you on that one. Say, when we talk about a static friction represented by that Fs, so that means a static friction is the frictional force on a stationary object that opposes the tendency of motion of the. So just know the static friction as the frictional force on an object which is not moving. Simple as that, honorable member. Whereby the formula, it remains to be that thing that is called mu. So we say mu s, that we multiply it by the normal force. Sometimes it can be written as that mu s, and then they write capital letter N. So that means the frictional force, it will be the calculation of that mu when you multiply it by the normal force. And then when it comes to the kinetic frictional force, that means it will be that Fk there. So that means here we will be having that mu again, but here with K, and then again you multiply it by that frictional, what is it? The normal force, I mean to say, yes, the normal force. Otherwise, sometimes it can still be written as this, or yourself can write it as that mu and then capital letter M for the normal force. Yes, something of that. So this normal force, honorable member, it is the one that I've just explained, where you are having this one under those circumstances, or you are having that one under those circumstances, is it? Oh yes, where's another one? Normal force, that one under those circumstances, that one being the normal force, and that one, yes, here we don't have normal force, yes. So that means this formula, the one that you're going to use the most is this one of kinetic, because we will be dealing with objects which might be moving. So that means the calculation of the kinetic friction, it will be that kinetic friction, which will be equals to your mu kinetic that you will be given. Remember, there's a decimal, then here you will substitute whatever normal force that you are having, depending on the situation, which could be those three situations that I've explained, where you might be having just mg there, if not mg, but mg minusing whatever, or mg plusing whatever. So that is what actually goes in there as you calculate your frictional force. So with regards to the mu, just think of that mu as it refers to the types of surfaces. Imagine having a gravel and then having a tar road. So obviously, you might find that maybe the mu here, it is something like 0.9, and then maybe the mu here, it is something like 0, maybe 3. Yes, just think of it as the roughness. It's like how smooth is the surface. If the surface, it is that rough, then you might find that you've got that higher mu. But if maybe the surface is smoother, you've got lower mu. Something of that nature, honorable member, where they can be talking about an object which is traveling on a gravel, and then you still have that same object traveling on the thing there. So they will definitely have different mu's. So with them having different mu's, that means they will end up having different kinetic frictional force. Why? Because that mu, it will be multiplied by that same normal force. Again, even if you do the calculation for this one, you are therefore going to have a different mu multiplying by the same normal force. Therefore, it means the frictional force of a different mu will definitely be a different frictional force of that different mu. So in most cases, you'll find that the mu, it is given to you, but what you need to figure out, it is this one, which is what I'll be teaching you on the next lesson, where we look at object in different situation where forces are acting differently. So I think I will leave it here for now and say until we meet again.